Should I start? Okay. So I'll begin with I'll start with giving a revision on what we call group before I then move into what we call rings. So a group is another pair, let's say G on an operation star satisfying the following properties. So the first property before we can call another pair a group is one, satisfies the associative property, and this is the associative property. And then secondly, there's an element E in G, an element, let's say E in G, called the identity element, such that for every A in G, A star E equals to E star A is equals to A, is the second. And then the third one, for each A in G, for each element A in G, there is an inverse element, let's say A inverse, such that A star A inverse equals to A inverse star A gives me my E. Here, my E is the identity element here. So another pair, this is a group, and a group is said to be another pair satisfying the following properties if it is associative, if there is an element E in G called the identity element such that this holds, and also if there is an inverse element such that this also holds. So if we are asked to prove, let's take for example, we are asked to prove that the set of positive integers is a group, we are looking to prove that the set of integers is associative, the set of integers have an identity element, and it also has an inverse element. So the information we are going to be needing, first one is we are going to show that is closure property, that's one. The second one is associative property. The third one is existence of identity element. And then the fourth one is existence of inverse inverse element. So all of these four is what we need to prove that the set of positive integers is a group. So I'll take it again. Another pair G, comma, this is the operation satisfying the following properties. So these properties, these three properties, once they are satisfied, then that particular set is said to be a group. The first one is closure property, second one is associative property, existence of identity element, and existence of inverse element. Now this now takes us to what we call rings. So I can clean the board. Now there is an extension of some properties in rings. For we to say a set satisfies it to be a ring, it doesn't just have to satisfy the closure property, it doesn't have to only satisfy the associative property. Third one, existence of inverse and existence of identity element. There are some other basic properties it also has to satisfy, which I'm going to be writing on the board. So a ring, a ring R is a non-empty set, is a non-empty set with two binary operations, with two binary operations, which is addition and multiplication, satisfying satisfying the following axioms. So the first one, let me call it 1a, is the closure property, which says that for all a comma b in R, a star b is also in R. Now, since the operation we are looking at in ring is addition and multiplication, because addition and multiplication are the operations under ring, so my operation here has to also be defined as a plus b is in R. This is closure property under addition. So I need to also define for multiplication also. So here I can say closure property under multiplication, which says that for all a comma b a member of R, a dot b is also a member of what? R. So when you're also defining your associative property also, you need to define it using these two binary operations. So next one, let's say 2 as associative property under addition, which says that for all a comma b comma c in R, a plus b plus c equals to a plus b plus c. This is under addition. Under multiplication, this just changed to a b c equals to a b times c. Commutativity. Now, if you are beginning to compare what we have, the properties we had in our group, together with what we have in our rings, there is no commutativity in group. So you have to take note of that. So this commutativity under addition is for all a comma b in R, a plus b is also equals to what? B plus a. Now commutativity only holds under addition. We have no multiplication under commutativity. Now we have the zero element, which says that there exists a zero in R such that for all a in R, a plus 0 equals to 0 plus a equals to a. And then we have for all a in R, there exists a plus minus a, which is equals to minus a plus a, which will be equals to 0. And the last one is the distributive element. The distributive property, distributivity, for all a comma b comma c in R, A open bracket B plus C equals to AB plus AC. This is left distributive, and then A plus B C equals to AC plus BC. We also prove this right distributive. So if you are asked to show, let's take for example, we are given the set R equals to A plus B root 2 such that A and B are integers. Show that this is a ring. So for we to show that this is a ring, we have to show that it satisfies this closure property, associative property, it is commutative under addition, existence of zero element, it has this distributive element, both left and right distributive. So I'll be using these properties here to solve this question. Might not be able to solve everything. I can just stop at zero element and then I can leave the rest as exercise for us to do. So anytime you're asked to show that a set is a group, we know what we want to show. One is the closure property, two is the associative property, three existence of inverse elements, and four existence of identity elements. So if you're asked to show that a given set is a ring, these are all the conditions we need to show. And take note, ring, the binary operation on that ring is addition and multiplication. So let's take an example. Now an exercise or an example. It said, given the set R equals to A plus B root 2 such that A comma B an integer, show that R is a ring. Show that this set R is a ring. So solution. So the first thing I'm going to be listing them here. Let me just make a line here. So the first thing I'm going to show is the closure property. The closure property under addition. Now, for me to show closure property under addition, remember the closure property says that for all A comma B in R, A plus B is also a member of what? R. That's closure property under addition. So I'm also going to do the same thing here. So I'm going to say let's say X comma Y be a member of R such that X will be equals to, I'm going to pick another set of integer m plus n root 2, and y will be p plus q root 2. So that I can use this definition here. A plus B is also a member of R. I need two elements. So I'm picking two elements here. So then I can say where m comma n comma p comma q are all integers, like it's been said here. A and B are integers, so I'm going to define my m, n, p, and q as also integers. So closure property under addition, that will be x plus y, which will be equals to, my x is m plus n root 2 plus y, which is p plus q root 2, and this will be m plus p plus n root 2 plus q root 2. And this is m plus p plus root 2 n plus what? Q. Now, since x plus y is in R, x plus y is in R, since m plus p, this will give me an integer, and also n plus q here will also give me an integer. So I've been able to show that this satisfies the closure property under addition. The second one I want to show is the associative property. The associative property under addition, and associative property is saying a comma b comma c now equals to what? A plus b plus c equals to a plus b plus what? C. So I'm going to follow what I've written here. Now here, I'm going to need one more element. Because here I've said x and y, so I'll need one more element here. So I can say this one, I'll call this one 2. I've picked x, y, let me pick z. Let z equals to I plus j root 2. So what I'll be doing here in my associative property is I'm going to show that this left hand side is equal to this right hand side. Okay, so what I'm going to do here is, so we want to show that x plus y, that is, I don't need to define my x and y again since I've defined it from the beginning. So x plus y plus z equals to x plus y plus z. So this is what I want to show. I want to show that this is equals to this. So my x plus y already, no, sorry, x plus y plus z. So I've gotten my x plus y from here already. I can just plug it in here and get for the left hand side. The left hand side, which is x plus y plus z, will be m plus p plus root 2 open bracket m plus q plus our z is I plus j root 2. So I can say this will be equals to m plus p plus I plus n plus q plus j root 2, because m plus p plus I will give you an integer. Also, n plus q plus j will give you an what? Integer. So my left hand side is m plus p plus I plus n plus q plus j root 2, which means that what I got here is also what I should get on my right hand side. So if I also compute this x plus y plus z, it must also give me this. So what I'm going to compute first is this y plus z. So if I compute y plus z, my y is p plus q root 2 plus my z, which has been defined as I plus j root 2. So I'm going to have p plus I plus root 2 open bracket q plus j. So this is y plus z. Now add it to y. So x plus y plus z equals to, my x is m plus n root 2 plus y plus z, that is p plus I plus root 2 open bracket q plus j. So from here, this will be m plus p. So let's expand. We have m plus n root 2 plus p plus I plus root 2 q plus root 2 j. So this can be written as m plus p plus I. Now here I have root 2, I have root 2, I have root 2. I can factorize out my root 2, and then I have n plus q plus j. So when you compare with what I also have here, this basically means that my left hand side, that's x plus y plus z, which gave me n plus p plus I plus n plus q plus j all into root 2. Same thing with this, n plus p plus I plus root 2n plus q plus j. I've been able to show associativity under addition. Now the second one I'm going to is the existence of zero element. So whenever we are asked to show that a set is a ring, all we just do is just to follow the properties that satisfy a ring. So I can clean the board. So this zero element is saying that there exists a zero in R such that for all A in R, A plus 0 equals to 0 plus A equals to A. So what we are going to do is to define what 0 is. So I can say 0 is equals to 0 plus 0 root 2. Then if I have A plus 0 equals to 0 plus A equals to A, so I'll say let A equals to m plus n root 2. So this will be m plus n root 2 plus 0, which is 0 plus 0 root 2, which is the same thing as saying 0 plus 0 root 2 plus a, which is m plus n root 2. So my main aim is to get back my a. So if I do this, I have m plus n root 2 plus 0 plus 0 root 2, which will give me m plus n root what? Root 2, which basically means that a plus 0 equals to 0 plus a is equal back to what? Equal back to a. So I've been able to prove my zero element. Now, the next one I move down to is my commutativity. Commutativity, note, always under addition. The closure property, we still need one more, multiplication. The associative property, we still need one more, which is multiplication. Our zero element is just for addition. Our commutativity is just for addition. So this is the fifth one. So commutativity, for all A, B in R, A plus B equals to what? B plus A. So this is what I want to prove. So fourth property, let's say A equals to m plus n root 2, B equals to, let me choose P plus Q root 2, or you can make your own. Let me make it x and y, since I've been using x and y, x, y. So I want to show that x plus y is equals to y plus x. So x plus y equals to m plus n root 2 plus y, which is p plus q root 2. And this will be m plus p plus root 2 n plus q. This is x plus y. Now y plus x will be p plus q root 2 plus x, which is m plus n root 2. And this will be p plus m plus root 2 is common here. and I can have q plus n. This can still be written as n plus p plus root 2 n plus what? Q. So x plus y equals to y plus x. So I've been able to prove closure property under addition, associativity under addition, existence of zero element, commutative property. Now the fourth one I want to go into is closure property, under multiplication, that says that for all a comma b in R, a b is also a member of what? Of R. So here I'm using my definition of x and y. So anytime you're asked to, first thing first, if you are giving this in the exam, the first thing you have to do is to define what a ring is. So the first thing you have to do is to define all the properties that satisfy a ring. Then you now start taking each properties and then you now start showing them one by one. So closure property, my x is n plus n with 2. My y is p plus q root 2. So x dot y, that will be n plus n root 2 multiplying what? P plus q root 2. So you have m times p, that's mp plus mq root 2 plus np root 2 plus nq multiplied by 2, because root 2 times root 2 is root 4, square root of 4 is 2. So you have mp plus root 2 nq plus np plus 2 nq. Now I can say equals to np plus 2nq plus nq plus np root 2. Now for whatever you are proving, it must always be in this form. Now if you add this, mp plus 2nq will give us an integer, because we've defined from the beginning that m, n, p, and q are what? Integers. So addition of integer will also give an integer. Also this here, mq plus np will also give an what? Will also give an integer. So by the time you add this together, let's say it gives you, let's say f, and then this one you add it together, it gives you what? Let's say g. I can basically write this as f plus g root what? Root 2, which is still looking like this in this form. So we've been able to show that commutative closure property under multiplication. Now the next one we are moving to is associativity under multiplication. Associativity under multiplication. So for all a comma b comma c in R, that's a times b times c equals to a times b times what? C. So same way I showed my associativity under addition, where left hand side is equals to right hand side, I'm also going to do this. Let me list the remaining here. Next one is for all a in R, there exists a plus minus a equals to minus a plus a, which will be equals to 0. And the last one I gave was distributive. So all these properties must be proved before we can say that this given set here is a ring. So I'm going to stop here and then leave this remaining two as exercises for us. So associativity, as I'm using x plus y plus z equals to x plus y plus z. Now if you can recall what x plus y is, We said x is n plus n root 2, y is p plus q root 2, and our z was I plus j root 2. So let's tackle the multiplication. Sorry. This is associativity under multiplication. XYZ equals to XYZ. We've proved from the beginning associativity for addition. I think we've proved this. This is the next one we are going to. So XY will be n plus n root 2 multiplied by p plus q root 2. I think we've been able to show x times y here, which is np plus 2nq plus nq plus np root 2. So this is what our x times y is. Let's multiply it with z, which is I plus j root 2. So if I use I to multiply all of this, I will have npi plus 2nqi plus nqi plus npi root 2 plus, use this to multiply all of this, you have j times this, that is npj root 2 plus 2nqj root 2 plus nqj plus npj times what? Times 2. So I can have 1, 2, 3, 4. npi plus 2nqi plus nqj plus 2npj, and then I can bring the ones of root 2 together. That will be plus root 2 open bracket nqi plus npi plus npj plus 2nqj together. So since m, n, q, I, j, p are all integers, addition of all of this will also be an integer. Addition of all of this will also be an integer. So I'm looking to get this also on my right hand side. So remember, you don't have to keep saying all of this all the time. So since we said it from the beginning, when we were defining our x, y, that was when we were doing when we started with closure property, we defined our x and y, and we told them that m, n, p, and q are integers. Then when we got to associative property, where we needed one extra element also, we also defined our I and j. So we've defined this from the beginning, so we don't need to keep defining it again. So the right hand side, you have y times z. Let's do y z first. So my y is p plus q root 2 multiplying z I plus j root 2. This will be pi plus pj root 2 plus qi root 2 plus qj times 2. And this will be pi plus 2qj, pi plus 2qj plus pj plus qi root 2. So if I'm to multiply all of this with x, all multiplied by x, which is n plus n root 2. So this will be m times pi, that will give me npi plus 2mqj plus mpj plus mqi into root 2. Then if I use this also to multiply all of this, I will have npi root 2 plus this multiplied by this would be 2 okay, n times pi, that's npi, n times this I npi 2nqj, yes, and then j. Okay, I'm supposed to, there's a mistake somewhere. I get my mistake. So here I'm going to have mpi plus 2nqi plus mqj plus 2npj plus root 2 all into, I have root 2, that's nqi plus npi. Here I have root 2, that's npj. I have root 2 here, I'll be left with 2nq. So this was what I'm supposed to get. Okay, so let's move on. So we have m times mpi 2mqj mpi root 2, this times this, and then this times this. This will be 2nqj root 2. So when we start looking at what we have, we can see that it's okay. So we have, I'm seeing mpi, I'm seeing mpj mqi, mpj mqi, I'm seeing 2nqj, I'm seeing mpi. So all of this I've seen it. So if I can just say nqj plus nqi times times 2. So I can say root 2. Yeah, I have root 2 here. That's mpj plus nqi plus npi plus 2nqj. So I have mpj, nqi, npi, 2nqj. This has been settled, plus npi plus 2nqi, npi 2nqi, 2npj, n so plus npi 2nqi plus 2nqj, 2nqj, and then the last one, 1 2 3 4, 1 npi 2nqj, nqj, and npj times 2. So let's trace back our mistakes. MPI, 2MQJ, MPJ, MQI. Oh, there's supposed to be this 2 here. Put 2 times the 2. That will be 2. 2 should multiply this. MPJ, MQI, with 2, that should be 2, plus with 2 times this as with 2 NPI, 2 NQJ, M2, plus with 2 NPI, 2 QJ, then this should be 2. MPI, 2 MQJ, MPJ, so mistake, plus MPJ plus MQI all into 2 plus MPI root 2 plus 2 root 2 NQJ plus this root 2 times root 2 will give me 2. Then n times this will be NPJ plus NQI. So I have MPI plus, and I see 2 NQI here, 2 NQI plus 2 NPJ plus, and I see NQJ, okay, plus root 2 open bracket NPI plus MPJ plus NQI plus 2NQJ. So the only thing, we've seen this, which is the same thing as this. I'm seeing MPI, 2NQI, 2NPJ. The only one I've not seen is this. So where is our mistake coming from? MPI plus NPI with 2 plus 2 NQJ plus MPI, 2NQJ. I have 2NQJ. So the only thing different here, is just this. Probably there's a mistake somewhere. Okay. So let's not dwell on that. We are supposed to be getting the same thing here. This is just the main issue. So you guys can detect that. So I've been able to show the associativity for multiplication. So I'm going to leave this remaining 2 as exercise for you. So you are going to give me a minus a. Define your minus a, and then you add. So you can just say let a equals to x plus y with 2, minus a should be minus x minus y with 2. Then you have a plus minus a equals to minus a plus a, which will be equals to x plus y root 2. That's your a. And then your plus minus a, that's minus x minus y root 2. This will give you 0. This other side also should give you 0. And then you can do the distributive, go the left distributive and then right distributive. So anytime you're asked to show that a set is a ring, first thing first, closure property. You can decide to write it closure property under addition. Number two, closure property under multiplication. Associativity under addition. Associativity under multiplication. Existence of zero element. Commutativity only under addition. Um, and then you show your distributivity, and then you also show this. So anytime you're asked to do anything like this, the first thing you have to do is always define what ring is. The first one I saw was group. So before you can show me that a set given is a group, define what a group is. Then you pick each property satisfying a group, and then you start showing that this particular set satisfies each of them. Then at the end of the day, you can now say the given set R, that is this given set R is a ring. If it does not satisfy any one of these property, then it is not a ring. Let's assume we're able to show that this is correct, 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 this, and then there was a fault here. This is not a ring. So it must satisfy all the properties of a ring. So I've given this as an assignment for us to do. I think I have one that you can just try. Boom, boom, boom. Okay, I can't see it, so let's just stop there. So far we've been able to talk about what a ring is. First thing, we started with a group. We talked about what a ring is. I said there are some properties that has to be satisfied for you to call a set a group. First one is closure property. So you need to define what a closure property is. For all a comma b in R, a plus b is also in what? In R. So you notice that our closure property here is only in addition. Unlike ring, where we have closure property for both addition and multiplication. So the binary operation we use under group is addition. So you have to take note of that. So the second one we also proved was associativity. If you take note also, we also only use the addition, if I'm correct. So I said for all a comma b comma c in R, a star b star c is equals to a star b star c. And then we said existence of identity element, also existence of inverse element. Then when we talked about a ring, we added some extra properties like closure property under multiplication, associativity under multiplication. Now you are going to take note that when you look at these two properties, we really didn't make mention of it here except for except for I think this. So I'm going to give you the reason why we didn't really make mention of that in the next class. So 4, we talked about distributive, addition, multiplication. We talked about commutative property under addition. We said something on distributive, and then we made mention of this zero element. So when you count the number of properties it has to satisfy for it to be a ring, you have 1, 2, 3, 4, 5, 6, 7, 8. I think 8 properties before we can say a particular set is a ring. So some of the keynotes I said was, if you are given a set and you are told to prove that it's a group, first thing you do is to define what a group is.